Easy, James here. Now, balanced audio. Now, there's a lot of other guys on YouTube who are doing videos about DJing and audio advice and just general tutorials. And some point during their videos, they've all referenced to something called balanced audio. Now, the problem is they haven't actually explained what balanced audio is. So I feel like it's my duty to provide you with the information about what balanced audio is, how it works, and why you should or shouldn't use balanced audio in your setup. Now, before you can understand how balanced audio works, you need to understand how unbalanced audio works. And before you can understand that, you need to understand how audio actually travels through an audio cable. So we'll include all of that in the video. So this video is aimed for those of you who don't understand what it is and want to learn a bit more about what balanced audio actually is. So that better not be some pillock asking me if I want my patio pressure washed, because I'll take the leaflet and shove it right where the sun don't shine. It was actually a delivery. So this would be my new trainers. Oh, look at them. God, they're a bit sexy, aren't they? Nice Adidas. God, they're light. Don't weigh anything. What are they made of? Helium? Awesome. They actually look a bit better in real life than they do on the picture when I ordered them. Nice. Anyway, enough of that crap. We've got balanced audio to learn about. Come on, let's get to it. Right now, sound waves are basically just vibrating air. So the sound waves travel through the air and it vibrates the air molecules, which eventually gets to your eardrums, which vibrate, and then you hear sound. Now, we all know that. We learnt that kind of crap in year 4 in school. Now, in the case of audio, obviously the speaker will vibrate the air and that's how you hear the sound. Now, you can't obviously just send those vibrations down an audio cable unless you've got 2 baked bean cans and a bit of string. But if you actually want to send music down a cable, you have to represent those vibrations differently. Now, this is a typical unbalanced audio cable, and this will probably look very familiar to most of you. Now, in the name of science, I'm actually going to snip this now, and I'll give you a closer look inside the actual cable. I've stripped some of the insulation off the end of this cable so you can see what's inside it. Now, there's 2 parts to this. There's this inner conductor here, which is actually individually sheathed. It's got its own insulation on it. And there's this copper braid which goes around the outside of this inner conductor. Now, this copper braid actually connects to the ground on your equipment, and this is known as the sleeve or the shield. Okay, now the reason why this is called the shield is because it goes around the outside of the inner conductor and actually shields it because it's quite sensitive to noise. So it's basically like a barrier against noise on the outside of the cable. And that's it really. And sometimes there's some extra foil layers in here and sometimes some extra screening, but this one doesn't. This just has a single screened inner conductor and the shield. Right, now what I've drawn on the board here is the basic construction of the cable that I just cut and showed you. So you have the inner conductor and you have this outer conductor. Now the outer conductor is called ground, and this is the symbol for ground, as you might recognise it. Now your equipment basically sees this ground as 0 volts, okay? Now whether it is or isn't actually at 0 volts, your equipment will consider that to be 0 volts. So it's kind of a reference, and we'll get to that in a minute. Now this inner conductor is where your audio is actually going through. Well, now I've drawn a little chart here just so I can show you what happens with this centre conductor. Now the way it represents the sound waves is to use a varying AC voltage through this. Now this point here is 0 volts, okay, so this line through the middle is 0. This top part here is positive and this bottom part is negative, okay. Now let's just imagine a basic sound wave, what you would imagine if you could see a sound wave. It's just like that, okay, so just a basic sound wave, kind of like a swimming sperm. I don't know what that was meant to be, but yeah. So basically we'll just draw that. Right, now I've drawn our basic sperm swimming sound wave on this chart here. Now if you remember, this centre line is 0 volts. Now let's say for argument's sake that this point here is 1 volt, okay, and this bottom point here is minus 1 volts, okay. So remember, this is positive, this is negative. So our sound wave will go up here to 1 volt, then it will drop back down to 0, then it will go to -1 volt and back up to 0. Right, now this waveform here would make your speaker move outwards, then back to the beginning, then backwards, then back to the beginning. Now if you repeat that over and over again very fast, your speaker would move in and out like this. That vibrates the air, and there's your sound wave. Right, now the height of this waveform, so that would be from this point here to this point here, is called your amplitude. Right, now the time it takes to complete this cycle determines its frequency. Now frequency is measured in hertz, okay, and hertz basically means times per second. So let's say for argument's sake this point here to this point here is 1 second, so it's taken 1 second for it to do that. That would be 1 hertz, 1 time per second. Now let's imagine it does this 100 times every second. That would be 100 hertz, or 100 times per second. And obviously if it's 1,000 times per second, that would be 1,000 hertz, or 1 kilohertz. So this varying voltage here is travelling through this middle conductor. Now this outside conductor just represents the 0 volts. So your audio equipment, whatever that might be, so let's say your source is an iPod, and let's say your destination is, I don't know, an amplifier. Now your amplifier will use this point as a reference, so it knows what to compare this waveform to. It knows where the 0 point is. Think of it like this. You imagine if I draw a line here like this and I said, right, put your finger 2 inches above that line. You go, okay, well that's easy. I'll put my finger there. Okay. Now imagine I said, put your finger 2 inches below that line. You go, okay, I'll put it there. Now let's get rid of that line altogether. And now imagine I said to you, put your finger at 2 inches. You'd go 2 inches from what? The floor, ceiling, wall, what? Right, now enough boring board theory. Let's get on and do something interesting. Okay, now what you're looking at there is a waveform being measured on an oscilloscope. And this waveform is much like the one we drew on the whiteboard a minute ago. And I'm running this through 1 meter of audio cable. Okay, so that's fine. So as you can see, this system works, it's fine. But now let's say we want to pass it through, I don't know, 25 meters of audio cable. So let's try that. Oh dear, as you can see, we haven't got our nice clean waveform anymore. As you can see, the waveform's got a lot of kind of fuzziness around the outside of it. And that fuzziness is actually noise, and that noise is being overlaid onto our signal because we're running through such a long length of cable, and that cable is acting as an antenna and picking up noise. Now if we actually zoom in a little bit here, you can actually start to see the noise on a single part of the waveform, and it's quite a lot. I mean, if you look at it, we're at 50 millivolts per division. I mean, you know, you're talking, we've probably got 10 millivolts peak to peak of noise on there, and that's quite a big deal. I mean, that's definitely audible, and that's going to start to get actually louder than some parts of your audio signal. So as you can see, we've kind of hit the limitations of what our unbalanced audio setup can actually achieve. Now, what if we want to pass audio through, 25, even 50 meters of cable without having any noise on our signal? Can it be done? Well, yes, it can. This is where you need to use balanced audio. So let me show you what balanced audio can actually achieve. Okay, so we've got our nice clean waveform back again. Now, bearing in mind, this is the same waveform traveling down the same 25 meter cable, but this time it's traveling as a balanced configuration. And as you can see, no noise, and we've actually doubled our amplitude. We was running at 50 millivolts with the unbalanced system. We've now got it up to 100 millivolts. So how has it done that? How has it got rid of all of that noise and actually given us a louder signal than before? Well, that's the joy of balanced audio. So now I'll show you how it works. Right, now this is a typical balanced audio cable, and this one happens to be an XLR type one. Now you can also get these in a 1/4 inch jack type as well, but this one just happens to be XLR. Now unfortunately, in the name of science, I am also going to mutilate this one as well, but I can now give you a closer look inside the cable. Okay, there's actually 3 parts to a balanced audio cable. You still have the outer ground shield, and you also have 2 inner conductors as well. and these two inner conductors are actually twisted together to form a twisted pair. Now the reason why they do that is because you want these two cables to be as close to each other as possible, so that if any noise actually gets to the cables, it gets to both of them equally, and it will become clear in a minute why you want that to happen. But they're basically just two individually sheathed insulated cables, and they're right in the middle of this ground shield. Right, now I've drawn the diagram of a balanced audio cable, and from when I cut it open a minute ago, you'll know that there's two conductors inside there. Now these conductors are sometimes known as hot and cold. They're also known as inverted and non-inverted, and they're usually marked with a plus and a negative. Now what they're actually called doesn't really matter as long as you understand what's going on with these cables. Now these aren't really different to an unbalanced audio cable, it's just that there's two of them, but I'll draw out the same chart that I drew earlier so that you can see what's actually going on with these conductors. Right, so I've drawn out a chart much like before, and we've got two waveforms on this one, and I've labelled them hot and cold to correspond to our hot and cold conductors inside our cable. Now there's actually two signals travelling inside this cable, one on each of these conductors, and this is where a lot of people get confused. They think just because there's two conductors and two signals, this is a stereo cable, and it's not a stereo signal. Even though there's two signals, it's still mono, it's the same signal played down both cables. But our signals are 180 degrees out of phase from one another. So when one goes positive, the other one goes negative, and vice versa. So it's just basically inverted or non-inverted and inverted. That's it. Now one thing to note is, with a balanced audio configuration, unlike an unbalanced cable, this ground connection here is actually not necessary. It's not mandatory, you don't need it. So if you get rid of the ground connection in the cable, your audio signal will actually still reach its destination perfectly fine. And the reason being is because these two signals are referenced from each other rather than referenced to ground. So when the signal gets to your destination piece of hardware, a thing called a differential amplifier will look at the difference between these two, and it will produce a waveform based on the combination of these two. So what I'm saying is basically, this one here that's inverted will get inverted again and played over the top of this signal. Now, as you can see, even with our balanced configuration, we still have that horrible noisy signal, but we have two of the horrible noisy signals, and they're exactly the same, but they're both 180 degrees out of phase from each other. Now, even though the audio is 180 degrees out of phase, the noise that's laid over the top of that signal isn't. They're both in phase, and that's very important to bear in mind when we come to convert this back into normal audio again. So any noise that's picked up by our cable is overlaid onto both signals identically, because both cables are sitting right next to each other and they both pick up the same noise. When the differential amplifier flips this one over onto the other one, and what we end up with is the two waveforms combined together to make a slightly bigger waveform. And if we could actually see the noise that's been got rid of, you'll see that the noise is basically played over the top of itself, but one inverted and one non-inverted. So basically it's a carbon copy played in opposites over the top of itself, and opposites actually cancel themselves out. So this noise is literally cancelling itself out, and you end up with a clean signal that comes out the other side. Now that's pretty cool, you've got to admit. I mean, alright, it's basic physics, but that's pretty clever, whoever thought of doing that. Now there are other situations where this technique is used. One example of which is telephone lines, like your normal BT landline, actually uses this technique to transmit your voice signals down the telephone lines, because telephone lines are unshielded cables, and we're talking you could be anything from 500 meters to 5 miles from your local telephone exchange. And if you had to transmit audio down a cable that long, you could only imagine how noisy the signal would be by the time it got to the other end. Now, telephone services used to use transformers to do this job, but now they all use at-source ISDN. But the analog section of your phone system, even to this day, still uses this technique. Another example of the use of this technique is the humble Ethernet cable. Now, you all know what these are. You use these to connect your modem or your router to your PC or whatever. And again, these are unshielded cables, and there's twisted pairs in there, one for transmit, one for receive, and they're balanced pairs. And the reason being is because, again, these are unshielded cables, and these could be run anything from 10, 15, even 50 meters at a time through stud walls and ceilings alongside all your other mains cables and all your other electrical garbage in your house. It's all inducing noise onto this cable. And if this was a single-ended cable, by the time the signal got to the other end, your laptop or your router wouldn't be able to make head or tail of the signal. It'd just be all discombobulated. And is that even a real word? Is discombobulated actually a real word? I've heard so many people say it. I want to know now. I'm going to find out if it's actually a real word, because I don't believe it is. I reckon it's one of them words that people just use. I don't even know how to spell it. I guess Google will know. Oh, okay, yeah, fair enough. It is a real word. It's recognised by Oxford Dictionary, so therefore it's a real word. Okay, fair enough. I sit corrected. There's a couple of other little things you can do with balanced audio cables. One of which is, as I mentioned before, the ground is not actually necessary in a balanced configuration to get your signal from one end to the other. So you can actually perform something called a ground lift and actually disconnect the ground connection between two bits of equipment. Now, the reason why you'd want to do that is to remove something called a ground loop, and I'll quickly go into now what a ground loop is and why it's sometimes a bit of a pain in the arse. So let's say you've got two bits of equipment. You've got a mixer and an amplifier. Now, both bits of equipment have metal chassis, so they're connected to mains earth in the plug via the mains lead, and they're bonded to the same potential. So now you connect your two bits of equipment with your audio cable. Now, the audio cable has a ground connection. Now, the term ground and earth are used interchangeably, but in general the term ground refers to the return path for the audio, and the term earth refers to the mains earth. Although technically the correct term is CPC, the term earth is still used. Inside most bits of equipment, the ground and the mains earth are actually connected together and they're at the same potential. So by connecting your audio cable between the two bits of equipment, we've basically formed a continuous loop in our ground system, hence ground loop. Now, by itself this doesn't normally cause an issue. The potential problem comes in when the two sockets feeding your bits of equipment are a great distance apart, or you're running one of them from a long 15 or 20 meter extension lead. The impedance difference in the earth connection, possibly coupled with a high value of ZS, can cause small potential differences to exist on the earth connections on the two bits of equipment. In most cases, this will mean that a small current will flow in the ground loop. In a balanced audio system, this is nothing to worry about, but it can cause problems on unbalanced parts of the system or even other bits of equipment that are connected to the system. So if you're getting mains hum or buzzing in your audio, it could be this loop causing the problem. So eliminate the loop in the ground system and the current stops flowing. Problem solved. Now, another thing you can do with balanced audio cables is provide something called phantom power. Now, this is mainly beneficial to the use of microphones, like this one, for example. Now, these kind of microphones need power to work. They have circuitry inside and you need to power it up. So when you plug in your audio cable in the bottom, you can actually provide power through this cable and still get the audio signal from your microphone to your preamp or your mixer. And that is called phantom power. So you send power back up the same cable that your audio signal from your microphone is going down, and they don't interfere with each other. Now that's pretty cool, and I'll quickly briefly explain how that works. Okay, so to demonstrate this, I've got our waveform again traveling through our cable, and what I'm going to do is I'm actually going to apply a DC voltage to this cable. Okay, so we'll apply the DC voltage now. And as you can see, the scope's obviously adjusting, and we have a flat line DC. And now, even though we've got this flat line DC, believe it or not, our audio signal is actually still there. It's just in amongst this DC here. You can't see it though, because the DC voltage is so high in relation to our audio signal that it's offset by the amount, and you just can't see the signal, but it's still there. So believe it or not, we actually now have an audio signal and a DC current going through the same cable. Now the problem is, what do you do when it gets to the other end? Because we want our audio system at the other end to ignore this DC offset. So all we do is we use a high pass filter to remove this DC offset. Okay, so I've just simply run that through a high pass RC filter, and it's removed the DC offset and we've got our signal back. But that DC current is still present on that cable, even though the audio system is now ignoring it because of that high pass filter. Okay, just a quick demonstration of this phantom power thing. I've got a 9-volt battery there, and I've got an audio signal that's coming from my laptop into there, and that's travelling down that wire there and going up there. There, I've got a little RC filter, and I've got the 2 crocodile clips going to power the LEDs, and I've also got on the other side of that filter a subwoofer and a speaker. And if I press play on the laptop, as you can hear, we've got audio. So we're passing audio and 9 volts DC to power them LEDs through the same cable. And that is phantom power. Genius. Now that's all the benefits to using balanced audio. Now there's no real cons except for maybe cost. Obviously the equipment's going to be more expensive, the microphones and your cabling is going to be more expensive. But if cost isn't an issue, then you've got nothing to lose. You might as well use it. But if you're on a bit of a tight budget, then you need to work out where you can get away with not using it. Now, obviously, noise immunity is its main feature. So try and work out where you can get away with not using it, where you're not going to induce noise onto an unbalanced cable. So, for example, maybe try and keep your amplifier rack as close as you can to your main mixing desk. Or, you know, just things like that, and try and keep all of your cabling away from power, so power strips and stuff like that. There's just a couple of myths which I want to put right about balanced audio. Now, one of which is that you can take 2 legs of a balanced pair and put them into 2 mono channels on your mixing desk, pan one hard left and one hard right, and you get the effect of plugging into a differential balanced input on your desk. That's totally not true. In fact, what you'll end up with is a left and right channel which are completely out of phase, and it will just sound really odd. You'll lose all of your low end, and if you're closer to one speaker than you are another, it will just start to sound really, really odd. So it's not a good thing to do, not advisable at all. Don't even try it. Now, another thing is the same sort of thing. Basically, you take the balance cable and you put it into a stereo input, so left and right, but that's exactly the same thing. Yet again, you've got 2 channels, left and right channels, that are out of phase, and you will still end up with the weird sound. Now, I'm not sure why you'd even want to try this, to be honest. Most equipment nowadays has got balanced differential inputs. Even like your cheapy Mackie and your Behringer desks have now all got balanced inputs on microphone channels, and even some cheapy DJ mixers have actually got at least 1 balanced input. So just use it. Why would you want to mess around trying to do something like that? If all the equipment nowadays has got the facility for it, just use it. Don't try and mess around and do all that crap, because it's not going to work. So there you go. I hope that's given you a bit more of an insight and an understanding about balanced audio. Now, if you've got any further questions about it, feel free to leave comments in the comments section below, and I'll get round to replying to that as soon as possible. And the kittens are in the background climbing up the curtains and ripping the wallpaper off and doing all kinds of bedlam. I don't understand how they've got so much energy. I really don't. But there you go. Anyway, so thank you for watching. Nice one. That didn't sound good. What are you doing?